In algebra, we've seen numbers and we've seen variables. Each individually, we could consider it as its own term. But we've also seen these two terms combined into one. For example, I've chosen 2 and x to represent my constant and variable respectively, but we've also seen 2x as a term that stands alone in many of the functions we've looked at. Here, in this example, I've only used one constant and one variable, but there's nothing stopping us from introducing more constants and more variables to form a single term. So let's say we took 3, 2, x, and y, which would simplify to 6xy. In this example, I've chosen 2 variables that are different letters and therefore represent different things. But I could have chosen 2 x's, which would simplify to 6x squared. And we could have scenarios where we have different letters, and each letter has a different amount other than just one. So maybe we have 6x squared, y to the third, and z to the fifth. This term here tells us that we have a 6, 2 x's, 3 y's, and 5 z's in that single term. Again, all these pieces are held together through multiplication. In the act of taking a constant or a variable or a combination of the two, or a combination of multiple constants, combination of multiple variables, as long as we're combining them through the operation of multiplication, that new singular term is what we refer to as a monomial. So mono, singular. Monomial is either a constant, so just a standalone number would be considered as a monomial, a single variable, or a combination of constants and variables. I'll say and or variables, right? Because we could just have a combination of constants, which would simplify to a single constant, or we could just look at a combination of multiple variables, say x and x. So there's no constant involved, but that still classifies as a monomial. Or as I showed you before, we could combine constants and variables. The key here is that the combination of these things must be done through the operation of multiplication. And the other important thing that we need to make sure is the case when identifying what a monomial is that our exponents need to be non-negative integers. And if you don't know what the integers are, non-negative would imply it's 0 and above, but this set, 0, 1, 2, 3, 4, and that would go on theoretically forever. So as long as our exponents are of the values that I have in these braces, then we have a monomial term. If we see fraction exponents, if we see negative exponents, that's going to imply that we're working with some other type of function. Okay, so it's important that we identify the exponents are non-negative integers when we're looking at monomials. So if we have monomials, we can combine those monomials through addition and subtraction. So let's say we take a monomial term. Let's call it c sub 0 for the constant term. Our variable raised to some exponent will say n. Okay, so n, we'll say, represents some, we'll say, non-negative integer. So 0, 1, 2, 3, 4, all the way up to some number, or it could go on forever. Now, that's our single monomial term. And we'll say c, and we'll say sub n is equal to our constant. So the subscript is going to change as we move along. So it's going to be c sub 1, c sub 2. And the reason why I'm staying with c and changing the subscript is that way we could represent as many as we want, as opposed to if I start changing the letters to say a, b, c, d, I'm limited to just the number of letters in the alphabet. So I'm going to use the same letter and change the subscript to indicate I'm working with a different constant. Now, here's a single monomial term. So let's label that. If we add on to it another monomial term, so c sub 1, we'll say the next constant. And let's say we have our variable and the exponent decreases by 1. So it's not the same exponent. And the reason why I want a different exponent is because if they were the same exponent, then they would be considered like terms, and therefore I could combine them, and I would no longer have two individual monomials pieced together by addition, but rather back to a single monomial. So the exponents are different, and they're decreasing by 1 in value as we move along. And we could keep going by attaching different monomial terms to each other. As long as these exponents are different, so we don't have like terms, and you'll see the subscripts of these constant values are changing. And these would keep going all the way to c sub n minus 1, x plus c sub n, x to the 0, which is just nothing. So we could have just a single constant on at the end. Now, this long string of monomials that are held together through addition, so this string here, is what we call a polynomial. So a multiple terms of monomials held together through addition. Now, why didn't I include subtraction? Because we can just think of subtraction as adding negatives. So if I just introduce a negative constant for any of these c terms that represent my constant values in the monomials, well then there's your subtraction scenario. So this whole string here is the polynomial. So let's write that down below. The polynomial is a monomial or many monomials combined through addition. And we'll make a note. Why isn't subtraction included? Subtraction, we'll just say equals adding negatives. So there's what a polynomial is. We take a monomial term. So a single monomial is also considered a polynomial, but we'll just define it as a monomial. And then if we attach one or more monomials to that single monomial, we have just formed a polynomial. And what you'll want to recognize are the various names for polynomials. And polynomials are named according to number of terms and degree. So let's do degree, number of terms. What's also important to recognize is because the name is based on degree and number of terms, we need to know how to identify a degree of a polynomial, or that of a monomial, let's say. The degree for a monomial is equal to the sum of the exponents in that term. Okay, so when you look at the monomial term, the degree is the sum of the exponents. So for instance, if I had 6x squared, this is degree 2. But if I had 6x squared y z to the 5th, if I added these exponents, 2 plus 1 plus 5, this is degree 8. So we're adding just the exponent values to identify the degree of the monomial. Now, because a polynomial is a string of monomials, all we have to do is look at all of the individual monomials And whatever monomial has the highest degree, the polynomial's degree is equivalent to that. So I should say polynomial is equal to the degree of the monomial with the greatest degree. That sounds repetitive. Perhaps I could have written that better, but to identify the degree of a polynomial, we just want to look at each individual monomial. Which one has the highest degree? That is the degree of the polynomial. So let's go through the different numbers. So it could be 0, 1, 2, 3, 4. Make a little chart here. 5, 6, and it could keep going. So in terms of degree, if it's 0 degree polynomial, so something where the exponents sum to 0, so there are no exponents present, that would just be a constant. So if we just have a single number, say 6, we could theoretically put x to the 0 there because anything to the 0 power is 1, and this is just 6. So you'll see anytime the sum is 0, we are left with just the constant term, so we refer to degree 0 terms as constants. Degree 1 is linear. 2 is quadratic. 3 is cubic. 4 is quartic. 5 is quintic. And then anything after that, so 6th degree or higher, we're just going to refer to it as that number degree. So 6th degree, 7th degree, 8th degree, all up to nth degree. So a 6th degree polynomial, say. Number of terms. If we have 0 terms, well, there's nothing there. So that's just an NA application, and we wouldn't even have a function to look at. If there's 1 term, we refer to it as a monomial, as we discussed before. So a single term, monomial. If we have 2 terms, that's a binomial. 3 terms is a trinomial. And then anything after 3, so 4 all the way to n number of terms, we just refer to as a polynomial. So poly meaning many. So we have introduced what the monomial is, how it is formed, and some conditions that are necessary to look at. Then we introduce the definition for the polynomial, how that is formed. It is just monomials added together. And now we've given names to define polynomials according to degree and number of terms. So the reason why that's important is if you see these terms, you want to know what type of polynomial is being referenced. And that's going to dictate things that we'll look at later in the course that we are interested in. And then we also introduce how do we identify degree for monomials and polynomials. So that will be the conclusion to the introduction to polynomials.